The Milky Way, a giant vortex of trillions of stars and planets, interconnected by invisible threads of omnipresent gravity. Almost at the very edge of this dazzling whirlpool, the solitary sun makes its way through the cosmic abyss. It is surrounded by glittering clusters and mysterious nebulae reflecting the light of thousands of stars. They're shrouded in dark clouds of cosmic dust that hide whole regions of the galaxy from prying eyes. There, in the ice-cold, unexplored depths, there lurk amazing anomalies that exist by their own laws and rules, harboring their own secrets. The human mind is hardly capable of appreciating this titanic scale. Still, we continue studying mind-boggling space structures and never fail to be amazed by the grandeur of our universe. And now it's time to make acquaintance of some of them. Our galaxy counts around 200 billion stars and not less than 1 trillion exoplanets. Each of these celestial bodies is unique and has its own peculiar properties. Among the stars of the Milky Way, there are some supergiants capable of swallowing up entire stellar systems, but also there are absolutely tiny ones, barely glimmering in the boundless abyss of space. Some of them are solitary, while others make pairs and even form complex systems made up of several various objects. Following the immutable laws of gravity, new glittering stellar clusters and majestic associations form in the Milky Way among dark nebulae and bubbles of red-hot hydrogen. If we look at an area of space within the radius of 50 light-years from our Sun, we will observe around 2,000 stars here. We've looked at some of the most notable ones before, such as the fast-going Barnard star, the mysterious Proxima Centauri, the shining Sirius, and the diverse multiple Castor star system. And so it means that today, it's high time to set out much further out there. Having left the solar system far behind, as it were, we will notice that it is in the so-called local bubble. This giant structure is an area of hot, rarefied hydrogen surrounded by a layer of cold cosmic dust. It is believed that it came into existence on several almost simultaneous supernovae, and to date, its diameter is anything bigger than 300 light-years. These structures are called supershells and may even go beyond the galactic disk. Our planet is in a part of the local bubble called the local interstellar cloud. Approximately in 8 million years' time, which is quite soon by space standards, our system will leave it to enter a larger area known as the Loop 1 bubble. This superbubble is located approximately at the center of our galaxy and is as big as ours. It is partially intertwined with the local bubble, and its boundaries are rather blurred, so it is hardly possible to determine the exact distance to it. Currently, this value is estimated in the range of 250 to 300 light-years. The center of this giant cosmic structure is located away from the vector of motion of the solar system and is about 500 light-years from Earth, near a bright star called Antares. One of the unusual and notable stars located near the conventional boundary of the two bubbles is Spica, also known as Alpha Virginis. This star is one of the brightest objects in the night sky of our planet and is easily discernible in it with the naked eye. Calculations show that Spica is about 250 light-years away and is a multiple star consisting of 5 objects. According to observations, 3 of the 5 components are distant stars, and none of them can be seen from Earth without the aid of optical instruments. The smallest of these, known as Spica B and Spica C, are very faint objects at the periphery of the system, and studying them is a bit of a challenge. Spica B is about 6,000 astronomical units away from the common mass center, while Spica C is even further away, at about 14,000 astronomical units. Another component, Spica AC, is very close to the center of the system and completes a full orbit around it approximately every 660 days. It is a blue-white star 4.4 times more massive than our Sun, and the radius of its orbit is about 4 astronomical units. Still, astronomers are mainly interested in a bright binary star, which is actually the one usually called Spica. Both of its components are located very close to each other, so much so that even the best modern telescopes are not able to distinguish them as separate objects. Such stars are called spectroscopic binaries, and the parameters of each star are calculated from periodic changes in the overall spectrum. This is how astronomers became aware that the main object of this system, referred to as Spica AA, is a large blue-white star. It is about 11.4 times more massive than our star, and its radius is about 7.5 times that of the Sun. At the same time, its surface temperature is over 25,000 Kelvin, which makes it more than 20,000 times brighter than the Sun. Thus, it is Spica AA that makes the main contribution to the total luminosity of the entire system. Its closest companion, Spica AB, is noticeably inferior in terms of luminosity. It is only 2,254 times brighter than our star. Its mass is 7.2 solar masses, and its radius is approximately 3.7 times bigger than that of our Sun. It is also known that Spica AB is a very hot star, with a surface temperature of 20,900 Kelvin, or about 20,600 degrees Celsius. According to calculations, the distance between the components is only 0.12 astronomical units. That is 4 times shorter than the distance between Mercury and the Sun. Such proximity leads to the fact that powerful gravity deforms them and gives them an elongated, elliptical shape. Spica's total spectrum has a very complex structure. Firstly, observations show that each of the components is a so-called beta Cephei type variable. The processes occurring in their interior cause the surface of such stars to constantly pulsate, with powerful shock waves running across the surface as a result. These pulsations are made up of dozens of clear rhythms, but it may not be easy to distinguish them. Secondly, each of these objects has its own rotational speed. Usually close twin systems synchronize their motion due to tidal forces. But in the case of Spica, either star spins with its own rhythm. Most likely, the lack of synchronization is accounted for by the small age of this binary star. According to calculations, it was born only 12.5 million years ago. However, we cannot completely dismiss the idea that the components of Spica were born in different places and later came to be attracted to each other. If current theories of stellar evolution are correct, then the main component of the system is no longer a main sequence star and is close to exhausting its thermonuclear fuel. It will soon begin to expand and cool down, which may lead to the flow of stellar matter to the second component. This process is called accretion, and it has a significant effect on both stars involved. Similarly, the smaller component increases in mass, which causes it to gradually become brighter, but it ends its life cycle more quickly. It is thought that within a few million years, this process will lead to a Type II supernova, and Spica is the closest candidate for this tremendous and rare event. Eventually, the internal energy of the larger of the stars will become insufficient to resist the inexorable gravitational collapse. at which point it will shrink and then explode, scattering the outer layers around. In all likelihood, the explosion will break the bond between the two stars, setting one of them free. In the end, instead of the bright binary star, there will remain just a tiny and very dense neutron star, virtually invisible in the optical range. Meanwhile, Loop 1 contains many other bright stars, including the giant Scorpius-Centaurus Association, which may count more than 2,000 stars, according to the latest estimation. According to the currently accepted hypothesis, it is here that several large stars went supernova almost simultaneously, about 15 million years ago. It is this event that caused the formation of a giant bubble of highly ionized hydrogen, known to us as Loop 1. Calculations show that the temperature of interstellar gas in this part of our galaxy is over 1 million Kelvin, but its density is very low. Only about 50,000 atoms can be found in a cubic meter of space. This is about 10 times less than the average for the Milky Way, and 100–200 times less than the near-Earth space. That is the space familiar to us, in which almost all satellites and orbital stations are located. Such a high temperature causes the gas inside the bubble to constantly create a very weak but high-frequency radiation background. Fortunately, potential life within it is not threatened, because the stellar wind of even the smallest star is able to deflect this radiation. If the radiation does reach the hypothetical exoplanet, the upper layers of the planet's atmosphere are also able to offer protection, absorbing the radiation successfully. In fact, the Scorpius-Centaurus Stellar Association extends far beyond the Loop 1 superbubble. For example, a massive, dense and dark nebula known as the Coalsack Nebula is part of it. From Earth, it can be made out as an impenetrable black spot in the constellation of the Southern Cross. It is particularly noticeable because it covers part of the Milky Way. This structure is adjacent to Loop 1 as its natural boundary and is a giant dust cloud. The Coalsack is located about 600 light-years away, and its diameter is estimated to be about 30–35 light-years. In Earth's night sky, it occupies 24.2 square degrees, which is 138 times the area of the full moon, or about a third of the total surface area of the Southern Cross. The nebula itself has almost no stars visible to the naked eye, but with the help of powerful telescopes, we can see some bright stars behind it. Their light is largely scattered as they pass through the dust cloud, so a lot of the information about the objects behind the Coalsack gets irretrievably lost. Calculations show that in a few million years, due to the rotation of the galaxy, this nebula will be illuminated by starlight and is likely to offer an incredibly beautiful sight, a giant multicolored spot in the night sky. And after a long time, after its own gravity compresses it sufficiently to trigger the formation of young stars, the Coalsack will transform into a sparkling open cluster. As we continue our flight through the Scorpius-Centaurus Association, we notice that most of its stars are located in the relatively clean and empty space of the giant bubble. At its fringes, however, a very different environment surrounds them. Here, cosmic dust accumulates, displaced by stellar winds, echoes of supernovae, and glowing, expanding hydrogen. It is here, 440 light-years from Earth, that a large, bright and young star known as Zeta Ophiuchi is making its way through the blurred cosmic nebula. This celestial body is a blue giant, about 20 times more massive than our Sun. Studies of its spectrum show that its average surface temperature is over 35,000 Kelvin, which means that its radiation peaks in the far ultraviolet range. Analyses of the object's motion show that it was once part of the Scorpius-Centaurus Association, but as a result of some event, left it and is now rapidly moving away. The cosmic dust surrounding the star absorbs and scatters much of the light it emits. Were it not for this phenomenon, Zeta Ophiuchi could be among the brightest stars in the night sky of the Earth. Due to its impressive size and temperature, it emits 74,000 times more energy than the Sun. Thanks to this, even now the star is not only clearly visible in the night sky, but is among the 100 brightest objects there. The movement of Zeta Ophiuchi, in combination with the most powerful stellar wind, forms a luminous shockwave that looks like a hemisphere, and it faces the direction of its flight. By the brightness of this cosmic phenomenon, we can determine the activity of the stellar wind. Calculations show that the star loses about 1.1 times 10 to the power of -7 solar masses per year. In other words, every 9 million years, the mass of one sun is ejected into the surrounding space. Observations of the spectrum of Zeta Ophiuchi show that its surface is intensely pulsating under the influence of shock waves generated by processes in the interior of the celestial body. In addition, this star is rotating very fast. It completes a full rotation in about 1 day. And the speed of matter at the equator of the celestial body reaches 400 kilometers per second. For this reason, the shape of Zeta Ophiuchi is far from spherical. While its equatorial radius is more than 9 times larger than that of the Sun, the polar radius barely reaches 7.5. The temperature of the star is also unevenly distributed, from 30,700 Kelvin at the equator to 39,000 Kelvin at the poles. In addition, calculations show that because of the ultra-fast rotation, the giant star is on the verge of collapse. If it rotated even a little faster, the force of inertia would tear it apart. Despite its age of 3 million years, which is young by cosmic standards, Zeta Ophiuchi has already passed the halfway point of its life, and will soon turn into a red giant before going supernova, leaving behind a neutron star. Just a little away from this giant star is an object that is radically opposite to it in terms of its properties. The distance from it to Earth is known only approximately, and according to calculations, is about 400 light-years. This celestial body is not visible from our planet with the naked eye, and therefore does not have a beautiful name. Instead, it is known under a bland tongue-twisting index, which is right here on the screen. This space object is a neutron star, a remnant of a burned-out star left after a supernova. Although its mass is greater than that of most stars, its size is comparable to that of a small asteroid. For this reason, this celestial body cannot be seen even in the most advanced optical telescopes. Still, it emits powerful X-ray pulses that can be detected at a distance of thousands of light-years. For a long time, astronomers did not know about the existence of such cosmic objects. Only with the advent of X-ray telescopes, which see the cosmos in a spectrum inaccessible to humans, were we able to detect them. In addition, neutron stars are very rare in the universe, about 1,000 times rarer than ordinary stars. Given all these facts, it is not surprising that the object we're talking about was discovered relatively late, in the 1990s to be more exact, and is still the closest representative of its class to Earth. Obviously, a specimen located that close provoked great interest among astronomers, as well as a desire to comprehensively study such an unusual space object. The first measurements showed an extremely high temperature of this body's surface, so for a long time it was considered a candidate for the role of a hypothetical quark star. But later, with the data significantly refined, the object turned out to be an ordinary neutron star. although very rare, very young and hot. This celestial body is believed to have formed after a supernova explosion about 1 million years ago. According to the latest data, its radius is about 12 kilometers, and its surface temperature is more than 250,000 Kelvin. This value seems incredible, because the absolute majority of neutron stars known to us have temperatures of only a few thousand Kelvin, which is comparable to ordinary stars. However, calculations confirmed by observations show that at the moment of their birth, these objects can be as hot as several million Kelvin. Subsequently, they cool down very quickly. So it's a great deal of luck to find such a hot neutron star located at a relatively short distance from Earth. By studying such objects, astronomers gain valuable insights into the evolution of these mysterious celestial bodies. Despite advanced theoretical models, many aspects of neutron star physics remain largely understudied. For example, according to calculations, the gravitational field of supercompact and supermassive objects should so strongly distort the surrounding space that their description requires adjusting the usual laws of physics. In the neighborhood of neutron stars, this distortion combines with extra strong magnetic fields to produce physical phenomena impossible in most of the universe. It was here, near the closest neutron star, that one such phenomenon, known as vacuum birefringence or the Euler-Heisenberg effect, was discovered. The phenomenon is this: when passing through a strong magnetic field in a region of high gravity, light deviates from its linear motion, splitting into many rays with different planes of polarization. It is noteworthy that this effect was first predicted theoretically, then reproduced in laboratories on Earth, and only as recently as in 2016 was it detected in nature, just near this neutron star. Currently, it remains the only object that reliably demonstrates this fantastic phenomenon, although in recent years there have been indirect signs of its detection in other similar celestial bodies. Of course, research of this amazing cosmic object continues, because there is still a lot we don't know about the structure and evolution of neutron stars. Meanwhile, almost in the opposite direction of the Scorpius-Centaurus Association and the superbubble surrounding it, there are two magnificent star clusters in the direction of the well-known constellation Taurus. The closest of these is the Hyades, about 150 light-years away. This cosmic structure is an open star cluster, about 650 million years old. Incidentally, it is half destroyed by the gravity of the Milky Way. At the time of its formation, its total mass was over 1,200 solar masses, but since then most of the stars have left the cluster. At present, the central part of the Hyades is a very dense cluster of closely spaced stars with a diameter of about 10 light-years. Around this core, there is a tidal zone with a radius of about 30 light-years, where a considerable number of stars is concentrated, with a total mass of about 250 solar masses. Also, from the main part of the Hyades, there extend two very long tails. Observations reveal their length to exceed 2,500 light-years. It is believed that the cause of their formation was the gravitational impact of the massive core of our galaxy on the cluster. One of these stellar streams is directed towards the center of the Milky Way, and the second one in the opposite direction, to the edge of the galactic disk. Although the Hyades have been known to humans since ancient times, these structures were discovered for certain only in 2018. This was possible thanks to analyzing the proper motion of a considerable number of stars, which were not previously thought to be part of the cluster. In total, there are more than 700 stars in the Hyades, with a combined mass of 435 solar masses. Among these stars, there are no large ones. Such objects would have completed their evolution and transformed into white dwarfs by now. Currently, The cluster is known to contain 4 red giants, gradually completing their life cycle, and 9 white dwarfs, which have already exhausted the reserves of thermonuclear fuel. In addition, 27 brown dwarfs have been discovered, peculiar objects too small to be stars and too large to be considered planets. More than a dozen stars can be seen in the cluster with the naked eye, and one of the most massive, bright and interesting members of the Hyades is Epsilon Tauri, also traditionally known as Iron, or the Northern Eye. This star is located about 150 light-years from Earth and is visible in the night sky without the aid of a telescope. It has already passed the main sequence stage and evolved into an orange giant with a helium core surrounded by a rarefied envelope, not very hot by stellar standards. At the moment, Iron has a mass 2.7 times that of the Sun and a radius 12.5 times that of the Sun. Its surface temperature is lower than that of the Sun and is about 4,900 Kelvin, or a little over 4,600 degrees Celsius. Due to this body's impressive size, its luminosity is 80 times that of our parent star. At the moment, Epsilon Tauri is one of the largest stars near which exoplanets have been discovered. The celestial body named Amateru was discovered in 2007 and was the first exoplanet discovered within an open star cluster. The object moves along a moderately elongated orbit around its parent star, completing it within roughly 645 days. The average distance between the planet and the center of the system is about 1.9 astronomical units, but due to the elongated trajectory, this can vary significantly with time. In addition, the proximity of other massive stars can perturb the motion of the celestial body. For example, in 2023, oscillatory deviations in the motion of this exoplanet were recorded, which is something that may be caused by the tidal influence of the parent star, or else the influence of neighboring stars. Amateru's mass is 7.6 times that of Jupiter, and its radius is 18% larger. Due to the intense brightness of the central star, the average calculated temperature of Amateru is quite high. It is 541 Kelvin, or 268 degrees Celsius. Thus, this celestial body may be classified as a hot superjupiter. It is also highly probable that there may be large satellites located near it, close to Mars or even Earth in size. However, the chance of these hypothetical celestial bodies being potentially habitable is small. Unfortunately, this system is at the final stage of its evolution, as the central star has almost exhausted its stellar fuel reserves. Soon it will shed its outer shells and transform into a white dwarf, with the surrounding planets either getting destroyed during this process or frozen as a result. In addition, after about 30 million years, the Hyades will lose gravitational binding and disintegrate completely. The stars that formed part of this constellation will scatter across the galaxy, and only indirect signs will indicate their common origin. If we travel deeper into the cosmic abyss, we will soon reach another major star cluster. It's about 445 light-years from Earth, and it's called the Pleiades. According to calculations, this open star cluster contains about 3,000 objects, with a total mass of more than 800 solar masses. However, to date, only 1,200 stars are catalogued, while the rest remain undiscovered. Among other things, about a quarter of the objects in the cluster are thought to be brown dwarfs, too dim and cold to be seen among their brighter neighbors. Calculations show that this cluster is 115 million years old, which is fairly old for such structures. It is estimated that 2/3 of the stars that once made it up have already left the cluster. The Pleiades were originally comparable in brightness and size to the Orion Nebula. Modeling shows that in 500 million years, there will be only a few hundred stars, most of them small and dim, such as red and brown dwarfs. And when the age of the cluster reaches 1 billion years, it will retain only a few dozen objects. If the Pleiades approach a massive object during that time, such as a gas and dust cloud or a globular cluster, the disintegration will run its course even faster. The brightest star in the cluster is Alcyone, also known as Eta Tauri. This object is located 440 light-years away from Earth and is a multiple star made up of 4 components. However, 3 of them are not visible to the naked eye. The main contributor to the luminosity of this system is the blue-white giant Alcyone A, which has a mass of about 6 solar masses. According to calculations, its radius is anything between 8.5 to 10 times that of our star. At the same time, analysis of the radiation of this star shows that it rotates around its own axis extremely fast. The speed of movement of the outer layers at the equator of the star reaches 215 kilometers per second, which is about 100 times more than the Sun. As a consequence, Alcyone A is highly deformed and has the shape of a flattened ellipsoid. The force of inertia, combined with a powerful stellar wind, causes particles to leave the surface of the object and collect in a ring-shaped hot nebula around its equator. The average surface temperature of the star is 12,250 Kelvin, but it is lower at the equator and much higher at the poles. This causes the star's luminosity to be also unevenly distributed across its disk. On average, Alcyone A is more than 2,000 times brighter than the Sun. According to modern models of stellar evolution, the age of this star is estimated at about 70 million years. This is much lower than the average age of the Pleiades, which is about 130 million years. This could mean that Alcyone A was captured by the cluster after its formation. Other components of the system are at a noticeably far distance from its center, 10,000 astronomical units or more. The stars, known as Alcyone B and C, are blue-white main sequence stars. The former can even be seen with the simplest optical devices, such as the most common binoculars. Alcyone C is remarkable for its luminosity, which changes with a surprisingly clear periodicity. During a period of 1 hour and 8 minutes, the luminosity of Alcyone C gradually increases by about 5%, and then slowly returns to its previous value. This phenomenon is associated with processes running in the star's interior, which generate periodic shock waves traveling along the surface. The fourth component of the system is Alcyone D, a white and yellow star slightly larger and more massive than the Sun. Speaking about the planetary systems of these stars, their search has not yet been successful. Perhaps they are in orbits inconvenient for observation, or were subjected to destructive tidal influence of nearby massive stars. Either way, the high activity of the parent stars would very likely make life on them impossible. A glance over the region around the solar system, with a radius of a few hundred light-years, will show that it contains not only a wide variety of stars, but also giant clouds of dark dust, bubbles of red-hot hydrogen, and other amazing objects. Further away, it is easy to see that this area is only a small patch of space on the edge of the tremendous galactic arm of Orion. Against the background of the entire Milky Way, it is almost invisible. Meanwhile, our galaxy itself is just a shining grain of sand among the gigantic clusters and bottomless voids that form the large-scale structure of the universe. It is difficult for the human mind to grasp and visualize this infinite variety of the cosmos, and even more difficult to accept that we may be seeing only a tiny part of it. Dear friends, this episode has been one of the biggest and most time-consuming in the history of our channel. We've been working really hard on it for several months. Thanks to your support, we do our best to enhance the quality of our videos to make them ever more exciting and meaningful. Every frame on this channel holds a little of our inspiration and hundreds of hours of hard work. If you like what we do, just give us thumbs up or leave some nice comments. Feel free to share our channel with your friends, and so more people will have a chance to touch space. And let's keep in touch.